Hello, friends. We're here for the beginning of week 8. So we are nearing the halfway point. And what that means is that we have PLC 8 this week for Friday. Now, I think as of right now, I don't think I've actually posted it, but have no fear. It will be up real soon. And the same is true with homework number 4. I am going to need to post that. And when will that happen? That'll happen today. That will post today, which is Tuesday. And so I'll get the finishing touches on that and figure out a timeline for that one. We'll see how we go. Other than that, we have spring break next week, so there will be no class at all next week. And then in addition to that, the Tuesday following spring break, if I'm not mistaken, is also a holiday. It's Cesar Chavez Day. So that means that after the end of this week, we'll do our 3 classes this week, we'll do our lab this week, and then after that, we won't be back until the Wednesday after spring break. Is that right? I believe that's right. All right, so you have a good solid break. So enjoy it. I guess that's worth writing down. Spring break next week. And so that means that we should pick up with the thermodynamics that we left off at, and that is that we were talking about the first law. We have been talking about work. My goal was to take a look at each term in the first law. That is to say, starting with the work, we're going to look at the heat, we're going to look at the internal energy. We've kind of been doing a little bit of all of them, but we've been looking at the work done during particular processes. I want to finish out talking about the processes themselves, because this set of 4 processes comprises basically the most common things that we see when modeling a thermodynamic system and its transitions between states. So what that means is that we have talked about the isobaric process. We've talked about the isovolumetric process, and we've talked about the isothermal process. Now, the reason we're doing that is because, like I said, for a lot of this stuff, when it comes to calculations, the backdrop is going to be the ideal gas. All right. Now, not all the time, but for a lot of the calculations, it will be. So looking at it from that standpoint, that pen's warm here. Isobaric. Isobaric is constant pressure. Isovolumetric is constant volume, and isothermal, of course, constant temperature. So one of the things that's going to be important for you to start doing is separating temperature and heat. Because what that means is, because we have a difference in the two, right? What it means is that when we talk about them in a casual sense, often heat and temperature are interchangeable. They're used interchangeably. But really, when it comes to physics, we want to make sure that we're trying to use them in the way that they're intended. And it's just the same thing with, if you think back to mechanics, it's the same thing with velocity and speed, right? Sometimes in a common sense, those are interchangeably used. And for us, we have to try and give them particular meanings so that when we're speaking about one or the other. We're saying, yeah, I know, I mean this quantity. It's the one that does this, not the one that does that, right? So the same is true with heat and temperature. Isothermal is constant temperature, but that doesn't mean heat is not being transferred. It just means the temperature is constant. So, and we'll delve into a little bit more of stuff like that today, but start trying to think about temperature as being related to the energy of the ideal gas, whereas heat is related to changing the temperature. Okay, so there's the temperature and what that means, and then there's the ways to change the temperature, and heat is one of them, work is another one. So there's that. We're gonna add one more in here, and it's the adiabatic process. And the adiabatic process is, in fact, the one in which no heat is transferred. So this gets back to a boundary situation whereby you could define the boundaries of your system to be adiabatic, meaning I don't want heat to come in or out. I could define them to be diathermal. I could define, which means heat can pass through them, but I can also define them in a work sense where I'm going to say rigid, fixed, right? Well, that's going to mean that all my processes are going to be this. So that's buried into this one. Whereas if I have one in which the boundaries are flexible, then I can talk about any of these three here, okay? So these are the set of four thermodynamic processes that comprise the modeling that we're going to do in terms of how a system gets from one state to another. So we've talked about isobaric, we've talked about the isovolumetric. We're going to return to those two particularly when we start looking at the heat transfer, but let's take another look at isothermal here, and let's do a little bit of an example with that. So just by way of reminder, so that means this one is that the work done is 0. If it's a fixed volume, then the work done is 0. And this one here is the one in which the heat transfer is 0, so that's Q equals 0. So we also have those kind of ways to think about it in terms of the first law. And as long as I'm doing it, if it's an ideal gas, delta E internal would be 0 in this one. If it's an ideal gas. Okay. So let's take a look at an isothermal process, and let's look at the work involved, because that's kind of the thing that we are starting off with. So here we have a PV diagram, and we have a system here, and isothermal looks like this, where this is a line, or this is a curve of constant temperature. I'll just call it TA. All right, it's some temperature. In this case, we also have a constant number of, and by the way, maybe I've said this, but in most of these situations, we are assuming that the amount of material is staying constant. And what that comprises is that we have basically a closed system. So if you look at this situation here, where I might just say, okay, I've got a piston and a cylinder here, and it's hooked to this canister. So the amount of air within the cylinder here, within the tubing here, and within the canister here is fixed, right? It's I can push this, it bounces back. Oops. Right? I can pull it up, it bounces back, and push it right. I can put this into hot and cold, and this will expand or contract accordingly. But the amount of air that I'm talking about within the system is fixed. I'm not allowing any of it in or out. And that is generally true with the systems that we're talking about here. So again, same situation. no material in or out across the boundaries. And so we're going to look at what happens when our system is taken from the A, let's say from the 1 state down here to the 2 state. So we'll call this volume 2, we'll call this volume 1, and it's going that way from left to right. Let's assume that volume 2 here is perhaps equal to 4 volume 1s, right? It's expanded by a factor of 4. It started off small and now it's big. All right, so a couple of questions that we might want to answer. Okay, number 1, what's the pressure at state 2 related to the pressure at state 1? Right? In other words, if I think about, well, here's my state 1, there's a pressure involved up here, pressure 1, and there's a pressure involved down here, this is pressure 2. How is pressure 2 related to pressure 1? Okay, maybe that's the first thing we can start investigating. Now, if we are, which we would be in this case, we're talking about our sample, which is an ideal gas in this case, fixed amount of material, I would say number of moles, if that makes sense, fixed number of particles. What that means is I can write the equation of state for both state 1 and state 2 individually, and I can relate them. So how can I do that? So here we are at state 1, and I've got pressure number 1 multiplying volume number 1, and that's equal to NR times TA. Okay, and now here I go to state 2, and I say, all right, I know that pressure is number 2, volume is number 2, N is the same, R is a constant, which we should talk about at some point, and the temperature is still equal to TA. Therefore, the right sides of both of these things, it's the same number, okay? Which must tell us that, in fact, the left sides are equal, okay? And that means that I can write that P1V1 is equal to P2 times V2. And I think this is known as Boyle's law? Something like that, that the pressures and the volumes are related like this when the temperature is constant. And the number of stuff is constant. Amount of stuff is constant. There's a number of these kind of laws that you can deduce from the ideal gas, but actually it's the reverse in chronology. They were instrumental in building the ideal gas equation of state. This PV equals nRT, where is it? Here, right? This PV equals nRT was actually built from previous knowledge of Boyle, who discovered this, and Charles, who discovered the volume temperature or the pressure temperature, and then Gay-Lussac, who investigated the other one. Anyways, there was 3 of them, and they built them all together and made this. So anyways, there's a little bit of history there. If I know this is true, then what I can do is imagine that since the volume expanded by a factor of 4, well, that's pretty simple in terms of figuring out what happened to the pressure. It means it must have dropped by a factor of 4 because P1 times V1 is a constant, and it has to equal P2 times V2. So if this goes up by 4, that goes down by 4. Therefore, P2 is equal to 1/4 of P1. So, okay, we know that. Let's try to figure out how much, and this is going to be a bit of a disguise. I'm going to tell you that right off the bat. Let's try and figure out how much heat was transferred going from state 1 to state 2. How much heat was transferred? Okay, well, let's take a look initially at what is likely going on with the piston cylinder, and then what does that mean in terms of the energy bar charts, okay? So let's do that. If I take a look at state 1, I'm drawing a cylinder which is fairly compressed, right? Volume is fairly small, pressure is big, and what's going to happen is that piston is going to rise, say, or expand, such that you might say, well, I've got this situation here. Maybe my piston is way down here. Okay, and there is gas in the cylinder here. Okay, and it's at some pressure. Not sure if you can see my dots. Well, maybe. Okay. Here we are at state 1. So the question is, how do we go from state 1 to state 2 at a constant temperature? Okay, because by the time I get to state 2, I'm expecting to see something that looks like this, where the piston is now way up here. I still have the same number of dots, right? All my gas is still within the cylinder. I don't know, maybe that's, I didn't count, but maybe that's about the right number. And we have the same temperature of the gas here as we did here. Right? So what's happening in order to create this expansion? Now, think about this for a minute. If I say that the gas expands, a couple of things might go through your mind. Number one, well, if it expands, that means the gas did work, right? The gas, which was super compressed right here, is pushing really hard on the piston and pushing it upwards. Okay. So the gas is doing work, right? Work is done by the gas. That means I'm expecting energy to be leaving the gas, right? Let's just say the gas is our system. So the energy of the gas is dropping due to the work that it's doing. But notice we want the temperature to remain constant. That means the internal energy of the gas should also remain constant. Okay, so if I'm thinking from a bar chart standpoint, I should have a certain amount of energy here. Right? This will be the internal energy at state 1. Okay. By the time I get to state 2, what do I expect? The same exact thing. I should be able to say the temperature is constant, therefore the energy of the gas, the energy of my ideal gas, is constant. I had just erased that delta E internal is 0 in an isothermal process if you're talking about ideal gases. So I've got this going on, but we know that work was done, right? So in the sense that I'm thinking of my system here, I know that my system is transferring energy out in the form of work. Right? There's work that is leaving the gas. Therefore, we have really only one possibility remaining to us by which we can solve this riddle, and that is we must be putting heat into the system, right? If I think of the first law, which tells me that the internal energy change is due to heat transferred and work done, I see no change in the internal energy, and I see work being done. If I want to make sure there's no change in the internal energy, I had better backfill, right? So I need to say that heat is going in here, right, at the exact same rate that work's being done, okay? So from this standpoint, what does that mean? It means I've put a flame under here, and that's transferring heat into the gas, which is then supplying the energy necessary for the work to be done, right? So any one of these taken in isolation would indicate that some different outcome was possible, right? This gas expanded and did work, and therefore it cooled off, but it didn't do that, because if it cooled off, it would have had less energy here. Instead, it has the same energy there as it does here, which means as it expands and loses energy, I have to fill that void. And so I fill it with the heat. All right. So when I'm in a situation like this and I'm asking how much heat is getting transferred, do you see that what I'm really asking is how much work is getting done, right? In an isothermal process, those two are the same. Okay. So there's a little bit of language going on here. Okay. Isothermal indicates that delta E internal equals 0, and therefore Q is equal to minus W by the first law. This is not showing up real well. Let's try a different pen. All right, Q is equal to minus W when you're talking about an isothermal process. Okay? So when asked for the heat in this situation, really you can analyze excuse me, you can analyze the work and then make the argument that it must have been the heat. So let's do that. Find Q means find W. So work done, we already know, is negative the integral of P with dV. And so what we need to do is integrate that. Because in the first, well, I erased my processes list here, but you remember that in the first one, the isobaric process, the pressure was constant. And that makes the integral really easy, right? The integral is just P comes out of the integral, and then you integrate and find that dV is the change in volume, right? The isovolumetric case was the one in which there wasn't even a change in the volume. So there's definitely no work being done in the isovolume case. Having done the situations where those two are taken care of, now the temperature is constant, but we have to be a little bit more discerning about how we're writing this. So if I go back to my ideal gas model here, the equation of state tells me that if I want pressure as a function of volume, I have to divide the volume across to the other side. And that means that I'm going to notice, as I did before, that this nR times T is actually a constant. So pressure as a function of volume is really some constant, right? The pressure is some constant divided by the volume. That means I can write this as negative integral of nRT, in this case it's TA, divided by V, and that's integrated dV. Okay. So in my limits, in order to make this a definite integral, I'm going to go from state 1 to state 2, and that means I'm going from volume 1 to 4 times volume 1. And I'm sorry, it's getting a little cramped up there. I'm not sure if you can quite see, but that's 4V1 up here and V1 down here. So those are the limits of the integration. And all I have to do is just do that. Knowing that nR times TA is a constant, that can come out of the integration, and it's really just a dV over V, which turns into a log. All right, so I'm going to get equal to negative nR TA, and I'm going to get natural log of V when it's evaluated at 4V1 divided by V1. In other words, the log of 4. Okay. Hopefully that's okay with everybody. The integration is negative. Okay. What does that tell us? Well, it tells us that work is leaving the system, right? This is my system inside the circle here, and work is going away and leaving from the system to go do something else. So you're welcome to mess around with the log and the negative sign. I don't think it brings any joy in doing that. I can hide the negative sign inside the log. I don't find that necessary. Because ultimately, what am I going to do anyway? I'm going to take it up here, and I'm going to say the heat is negative of this, so I'm going to be losing it. Okay, I'm going to be losing the negative sign anyways. Okay, that gives me the opportunity to say, therefore, the heat that was transferred must be equal to nR times TA times the log of 4. So in doing that, we have accomplished two things. Number one, during the isothermal process, remembering that Q and W are numerically the same, but should have opposite algebraic signs due to their relationship to the system, right? One leaving, one coming in. And also we've now found a mathematical expression for the work itself, and we've done the integration of a 1 over V, okay? So that's an isothermal. This is kind of the idea for isothermal work. It's going to look like this whenever you are sliding down one of these curves right here. Okay. All right. Good. So in that case, what we've got here is the ability now to talk a little bit about the adiabatic process. Let's do that. The adiabatic process, I'm really only wanting to sketch this out very casually at this point and maybe return to it a little bit more in depth later because of the way because of its utility, essentially. So what I want to do here is look at an adiabatic process. Okay, and now we know that we're not going to be going along this particular line, but what I am going to do is I'm going to draw in several of the isotherms here in order to give you an idea of what an adiabatic process looks like, right? We know the isobaric is flat that way. We know the isovolumetric's flat this way. That's curvy like that. What does the adiabatic look like? Well, it turns out it looks really similar to this, but is not quite the exact same thing. So let's do this. I'm going to draw a couple of these isothermal curves like this. And you find that they kind of come down and go like this. You got this big family of 1 over V curves. Okay, these are all isotherms. Okay, I might say that's T at A, this is T at B, T at C, T at D, whatever. As long as you're on one of those lines, you have constant temperature. Okay, so the question is, what does an adiabatic curve look like? Well, it crosses isotherms. In other words, I might start up here at temperature C, and if I'm going along adiabatically, it's sharper. Okay, so the adiabatic, it's a sharper curve. Actually, let me draw that a little bit less sharply. I'm not totally happy with the way I drew that. All right, so it's a little bit more like that. Okay. Feeling like I was kind of coming into this point a little bit too steeply. So anyways, it kind of curves down like this, right? That's an adiabatic. That's the one in which no heat is transferred. So if I go back to my piston cylinder device, okay, that's a situation where I don't have a flame underneath it. I can't have this. What I do have is insulation around the cylinder. Okay, I have some foam or air or something like that, which is causing the isolation of the gas, right, from heat being transferred in or out. Okay, so thinking about this situation, this would be a situation in which the gas is going to expand of its own accord, right? It's going to say, I'm really compressed, I'm pushing hard on the cylinder, on the piston, and I'm causing the piston to increase like this. The cylinder volume is increasing, and it goes up to here. By the time that happens, the gas is now cooler than it was, right, as it has dropped down to a lower temperature. So my bar chart now has to take away this Q that was in here, okay? And it also has to modify this final temperature because the internal energy has to be lower. All right, so for an adiabatic process, the internal energy is changing because the temperature is changing. This adiabat is crossing the isotherms, so we know that the energy changes, and the energy is changing due to only work being done, either in this case by the gas or done on the gas. Okay, now a great example of this is pumping up bicycle tires. Okay, whenever you pump up bicycle tires, it's basically an adiabatic process. The reason being, adiabatic happens because the process happens quickly enough that heat doesn't transfer. Heat transfer is actually a pretty slow process. It either goes into, especially when it's a gas, right? Because gases, how do they transfer heat? They have to actually hit each other, and that's a pretty slow process. Whereas if you had a solid, they could communicate with each other a lot quicker because they're bonded, okay? So when you pump the bicycle tires up, you like this, right? You do work on the gas by pushing the piston down, pushing the plunger in the thing, right? You do the opposite of this. You go like that, and you end up with this. So in other words, you put a lot of work in, and then if you do that, and then you go feel, because normally the bike pump casings are some type of aluminum or something pretty lightweight. If you put your hand around the bottom of the barrel, you'll find it's warm, okay? And it's warm because you did the exact opposite of this. You went that way, up, right? You started at a large volume and then you compressed, and what that did was it shot the temperature up because you didn't let any heat leave, okay? And since you didn't let any heat leave, all of that's now in the internal energy, and it's like going backwards this way, where the work is going in instead of out, okay? The bike pump. So that's one thing. Also, diesel engines will often use this, they use this as an igniter. And in other words, diesel engines may not have spark plugs in order to operate, simply because they're relying on the compression of the gas fuel mixture, the air fuel mixture, to be of such a large amount that by the time it gets all the way up, this adiabat, the temperature is so high it just combusts, right? So same idea. All right, so one offshoot of this is that the adiabatic process is useful if you have if you need to describe a fast happening thing, right? It's a fast happening process. It does not have to be, right? I just want to point that out. It doesn't have, but when you have something happening quickly, it's very often useful to describe it as an adiabatic. So this can be used to describe fast processes. And I don't have quite enough room there, but I wrote over there. So it can be describing fast processes. And the bike pump is the one that I usually return to in my mind when I'm thinking about this. Okay. So that's really all I want to say about the adiabatic process. I'll let you know that you can find the work for it. We might do that at a later time. It's not super important right now. Because ultimately what happens with the adiabatic is that compare it to what happens with an isotherm. With the isotherm, what we found was P multiplying V is a constant, right? And we took P and V at state 1 and P and V at state 2 and found that they should be the same value. So isotherm means that PV is equal to constant. Adiabatic is one in which it's not P times V, it's P times V to an exponent. P times V to the gamma is a constant. Where gamma is an exponent which is greater than 1. Okay, so I want to push off the issues of, well, what is gamma? How does it get to be this way? What do we know about this? I want to push that off to later. Okay, I want to do that at a later time. Not ready for that right now. However, we will return to that, and we will talk about why it's this and what the gamma factor is. All right. So those are the 4 processes. Those are the work done. Those are the works that are done by the 4. Well, in principle, you could use this to find work done. And again, later for this. But anyways, we could use that to find the work done. We did do it for the isothermal case. We've done it for the isobaric. We've done it for the isovolume. So that's at least 3 out of 4 is not bad right now. I want to go on and start talking a little bit more about the heat transfer itself and what happens when heat is transferred. So we kind of left, excuse me, we kind of left off a little bit with this last time when I was talking to you about heat going into a substance and increasing the temperature. And what happens when heat goes into a substance does not increase the temperature. So I want to talk about those 2 situations. All right. So having talked about the work done in the first law, let's talk about heat transfer in the first law. So I skipped ahead a little bit on this last time so that you had some background on the PLC question. Nonetheless, when heating a substance, I chart the temperature of the substance, and let's suppose I'm just going to take water for now, okay? I'm going to take water and I'm going to put this on a centigrade scale. And this is a time axis here, which is indicating how much energy is going in. Let's assume that the energy is going in at a constant rate. Okay, and I think I mentioned this last time, in which you have an oven, which is a 200-watt oven or a 300-watt oven, whatever it is, and the energy is going into the material at that constant rate. So this heating happens. The heating is constant rate heating. Okay, that means the wattage. If I have a sample of water, and suppose here at time 0 I start with the sample here at some temperature which is below freezing, it's ice. I heat it, okay, it heats up. Okay, this is the ice phase, and that kind of heating was what I called sensible heating last time. And why sensible? Because it changes the temperature. It results in a delta T. So that makes sense. Intuitively, if I have all this heat and I dump it into this thing, well, that thing should get hotter. I have heated this up. And indeed, that's what happens sometimes. So now I get to 0 centigrade and I find out that I'm still dumping heat in, but the temperature is not changing. So really what I find is now this is a situation where I am melting the ice and making it into liquid water. Okay, so that's known as a phase transition. melting ice, and that means it's a mixed phase during this time. In other words, I started with all solid water, and at some point I'm going to look back and I'm going to say, well, I've got some solid water and some liquid water. And eventually, by the end of this thing, I'm going to have all liquid water, and all of that liquid water is going to be at 0 centigrade. Okay, so it's almost like there's a valve or a one-way valve to the energy, right? Heat's coming in at a constant rate. It's almost, I don't know, the first thing that jumps to mind is like being at the airport security lines, right? People are coming in at a constant rate, and you're the person going, okay, go over to lane 1. Okay, you go over to lane 8. Oh, you have kids. You need to go here with the metal detector so you don't get the X-ray. Oh, you have I don't know, whatever. You got to go over here. So they're dividing people up into different lanes. And the same kind of thing happens when you're thinking about how does the energy go to different places. It's almost like the material is there. It's going, okay, right here, come on in energy, come on in energy. Okay, I'm still at -4 degrees, so all of the energy is going this way. It's going this way into heating up, heating up, heating up. Okay, -3, keep going, -2, keep going, -1, good, keep going, we're heating up. 0, wait, stop, that lane's closed, you got to go over this way. And now we're going to go into the melting lane, right? So the idea is that I'm now changing where the energy is going, or what its effects are going to be, really. And now it's going into not increasing the temperature, which would have been that way over there. It's going into changing the phase, which is this way over here. I don't know. Maybe that works, maybe it doesn't. Melting ice, this is known as the latent heat because it's hidden, okay? It's known as a latent heat. After I melt all the ice and it becomes all liquid, I then continue to heat it up. I am going to find that the slope is more shallow than that, so I'm not going up at this angle, which is what I started doing. I'm going to go up at this angle like that. So I have definitely, right, the liquid I find heats at a much slower rate than the solid does. Okay, let's just pretend that this is now 100 degrees. I'm going to now find that it does that same plateauing behavior, and then all of a sudden it starts taking off again. Okay, so I'm kind of truncating my drawing here out of space requirements, but the idea is that whenever I'll make this a bit longer. The idea is that whenever you have a phase change, you have a plateau. All right. So this is sensible heat. Once again, that's sensible heat in the liquid phase. And then this is sensible heat in the gas phase. It's way over here. And then the latent heat, this was melting ice, so the latent heat was for the melting ice. This is the latent heat for boiling. This is now boiling liquid. And that's equal to a latent heat. And they have fancy names. Right, this is the latent heat of vaporization. I was going to say latent heat of boiling, but that just yeah. No, if you want to be all classy, you say latent heat of vaporization. And then this is latent heat of fusion, because they're thinking of the opposite process, the freezing of it, right? It would be the same exact situation. The great thing about this diagram is it's reversible, right? I could have started here and then imagined a cooling off process, right? I don't know, imagine my time was going that way for some reason. Right, I would be cooling the gas off, cooling. It turns into a liquid, cooling, turns into a solid, cooling, right? I could do the exact same thing. This diagram is totally reversible. So the amounts of energy depend only on how much of the stuff you have. It doesn't depend on the temperatures unless you stop in the middle or something like that. But if I'm doing the whole amount, if I'm doing all of this and then I do it all back, it should be all the same. Okay. So we have to describe, in terms of heat transfers, regardless of how the heat gets there, whether it be from conduction or convection, whatever, it doesn't matter. The effects are either it changes the temperature or it doesn't. So let's start off with that and let's describe that first. If the heat goes in and changes the temperature, then it's a sensible heat, and what that means is we use what's called the specific heat, which is the more modern term for that. All right, so specific heat is a situation in which I think of this as the thermal inertia. Okay, in other words, actually, before we jump to specific heat, I should be talking about the heat capacity first. I should talk about the heat capacity. That's really better. That's a better analogy for thermal inertia. In other words, inertia meaning it's the tendency of an object under duress of a force to accelerate. How much tendency does this object have to accelerate when a force is applied to it? If it's a ping pong ball and I push the ping pong ball, really easy to get it going. If it's a Volkswagen, not so easy to get it going. So the idea is that even if I apply the same force, if it's a larger inertia, it doesn't pick up speed quite so quickly. So that's the situation mentally with what is the heat capacity. If I dump heat into something and it has a really large heat capacity, well, then the temperature increase is going to be really little. I could take large amounts of heat, dump it into this thing, and the temperature might just go up a little tiny bit. Right? Whereas if I take something which has a low heat capacity and I dump heat into it, we'll find huge temperature change, right? So different materials have different capacities for heat. How much heat do they hold before they start really changing temperature? Okay, and the way I worded that's not really even very good. You don't really hold heat, but how much heat can you put into something before it changes temperature? Now, it turns out liquid water is one of the largest heat capacities that there exists naturally. We can make stuff that's got a fairly high heat capacity, but naturally occurring liquid water is quite good. Air is not quite so good, right? It's less. It's not that bad, but it's not great. Metal, situation here, very low. I put in a little bit of heat and all of a sudden the temperature is changing drastically, okay? So heat capacity is really, we think of it, it's called capital C, so I'll put bars on the C. It's really how much heat can you put in for a given temperature change, right? So exactly the same idea as how much acceleration do you get when you apply a certain force. Same idea. Okay, so as to why that is, well, there are different reasons, but the point is materials have different heat capacities. So let's take that out even a little bit further, and now we'll go to the specific heat capacity, which really does isolate the material behavior of it. And that means what I'm going to do is I'm going to do it by mass. Okay, I'm going to do this by mass. So that's the heat capacity. Specific heat is unfortunately going to be known as little c, and it's the exact same as the heat capacity. It just has a 1/m in front of it. Right? That thing right there is the same as the heat capacity. It's just per mass. In other words, now it's a little bit easier to talk about it by material, because if I take a glass of water down to the ocean, or I take a glass and I dip it into the ocean and I have ocean water in my cup, and I bring it back up here and I say, what's the heat capacity of this? Well, the heat capacity is, compared to the ocean, is going to be really little. I can put in some heat and it will change temperature. If I put that same heat into the ocean, it will not change temperature. But if I say, okay, let's do it by mass, and I say, okay, suppose I have a cubic inch or cubic centimeter, right, of this material, and I put heat into it, whether it's out of the cup or whether it's out of the ocean, it'll have the same effect. Okay. The reason the heat capacity of the ocean is so huge is because of the mass of the ocean, not because of the material. Well, and because of the material, it's liquid water. So this helps us distinguish between materials. Okay. In other words, metals have really low specific heats. Liquid water has a really high specific heat. When we talk about latent heat, that's a situation in which the temperature does not change, so there's no delta T associated with it. Okay, latent heat here is described simply by how much energy do you have to put in order to change the phase. In other words, from liquid to solid, or from liquid to gas, or whatever you like. How much energy does it require per mass in order to change that? Okay, this is the amount of energy, we'll say it's the amount of energy per mass to change phase. Okay. And since we're only going to be talking about the basic three phases, solid, liquid, and gas, we only have two latent heat. Well, we could have three latent heats. We don't typically talk about subliming, which is right solid to gas, but you sure could if you're talking about carbon dioxide or something like that. So the latent heat is the amount of heat required to change a certain amount, say a gram or kilograms worth of this material from this phase into this phase. Okay. So those are the two heats that we're going to talk about. At least those are the effects of the heats that we're talking about. When you're thinking about how to make this jive with the airport security line picture that I was telling you about before, right? So it's almost as if when this is going on, right, all the energy is going into raising the temperature. We call that thermal. So it's almost as if this is thermal. There's a thermal energy system. And when the temperature is not at one of these, this for liquid water, this is 0 centigrade, 100 degrees centigrade. So if it's not at one of those phase change temperatures, then the energy is all going this way, right? Energy is coming in and it's going that way into the thermal energy system. When you are at one of these phase change temperatures, that door shuts and then you go into basically a bond energy system, okay? Because what's happening? When I'm going from solid to liquid, I'm taking the bonds between the water molecules and I'm just making them less rigid, right? Ice is a very solidly rigid structure. If I heat it and I find that it's still, I'm relaxing the bonds, but it's still going to stay connected, well, now I've got a liquid. And the reason I have a liquid is because the bonds are weaker. And now I have something that can flow around something, okay? If I take and I destroy the bonds completely, well, now I've turned it into a gas, and perhaps it is modeled as an ideal gas, okay? So that would be one reason why this plateau is so much smaller than this plateau, because the weakening of the bonds takes less energy than the complete destruction of the bonds, which is this situation here. I am taking these liquid bonds between molecules and I'm ripping them apart. Okay, that's why it takes a lot more energy. And for water, this plateau is like 7 times larger than this one in size. Okay, so we would call this thermal. We can call this thermal energy. And we can call this bond energy. So the heats go into changing thermal energies or bond energies. Okay. And it's just easier to think of it as it's either doing that or it's doing that. Okay. So it's like a valve. So if the thermal energy is closed, I'm changing state. If that door is closed, I'm increasing the temperature. And certainly there are cases in which the doors are both open at the same time. For example, if you take a cup of water and you leave it out on the counter for a couple of days, you will find it is gone. Okay, so at room temperature, things can still evaporate, right? So that means you can kind of have a phase change happening when you're not at the phase change temperature. So we'll talk more about that as well, but point being that we'll start by saying, what if it was just one door or the other? Okay, so let's suppose then that I have a situation where I'm going to do an experiment and I have an unknown metal. Now, this is a great way to identify materials, is with the specific heat. So let's suppose I heat this chunk of metal up and I dump it into a vat of liquid water and I measure temperatures, right? So let's work on finding, let's find what material, find the, all right, let's just do it this way. Let's find this, we're gonna find the specific heat of a material. And we're gonna ID it. Okay, so people have made charts of the specific heat capacities of lots of different materials. So that when you go do something, you're like, I wonder what this is, and you do an experiment and you say, oh, it comes out to be about this number. You can go look in the table and go, oh, it's one of these, right? It's right. It's the material with that specific heat because they're all pretty different for the most part. Okay, so let's assume that we have a big container. I've got a big vat of liquid water here, which would be perfect on a day like today. And we'll suppose that this is starting at a temperature of 20 centigrade. I'm then going to dump in this chunk of stuff, which is heated. It's heated metal, and it's, say, 80 centigrade. All right. So let's put in a couple of masses here. Let's suppose that we know that I have, say, 10 liters worth of water. All right. So let's put, let's do it's liquid water. Let's suppose I have 10 liters. This is a 10-liter container. And let's suppose that this, make it easy, let's suppose that this heated metal is 1 kilogram. Okay. Now, I'm going to take the temperature. I have a temperature probe in here, right? I'm going to take the temperature. I'm going to wait for the equilibrium to arrive, which is going to announce itself because the temperature will stop changing, right? Initially, what's going to happen? The water temperature is going to go up. Eventually, the water temperature is going to stop going up, and that's when you go up. This is it. All right, so let's find the equilibrium temperature, which is when both things are at the same temperature. Let's suppose that is just a touch of it. Let's suppose our equilibrium temperature is 21.3 centigrade. All right, so let's use this to find the specific heat of the chunk of stuff that I've dropped in here. Now, a couple of things about this. Liquid water's specific heat is generally taken as a known, okay? So the liquid water has not changed phase. The chunk of material here has not changed phase. So I'm not dealing with any of this, but only these, right? Specific heats. I'm also going to make the simplifying assumption that they exchanged heats with only each other, and that I'm going to ignore any possible evaporation of the liquid. I'm going to ignore any heat coming out from the sides of the container. I mean, ultimately, if I'm in a room that's about 20 centigrade, well, this is not going to provide a very big impetus for heat transfer anyway. Okay, but nonetheless, in order to simplify this problem so we don't have to think more about other ways that heat could leave, I'm going to put an insulator around this thing, and I'm going to put a lid on the top of it, right? So none of the heat's, it's only chunk of stuff to liquid, okay? So our assumption is that, assume that heat is exchanged only between these two items. The two substances. And that means I can write that the heat lost by the aluminum, or whatever this turns out it's going to be aluminum, whatever is heat lost by this metal is going to be the heat gained by the liquid water. So in other words, Q, which is lost by the metal, I already gave it away, but that's okay. It should be heat gained by the water. Okay, like so. Since there's no other heat transfers that I'm allowing, that's the only one that we can deal with. And therefore, since these heat transfers were only specific, they were only sensible, no heat, no phase changes, then I can write this as minus mass C and delta T evaluated for the metal and mass C delta T evaluated for the water. Okay. So the M here means the metal and the W means water. Now, I have to make sure that I know that this is M of the water, C of the water, and M of the metal, C of the metal, and they're not canceling out. Okay. The question here is find that. Find that heat capacity. All right. So we can solve for that fairly straightforwardly just by dividing everything else over to the other side and taking a look at the quantities. So here I've got C of the metal is then going to be equal to swing all of this stuff underneath. I'm going to have, I'm now going to put the W on each one of these just to make it a little bit easier to find out what's going on here. Mass of the metal, delta T of the metal, and I need a minus sign in here. Like so. All right. Now, with the numbers I have, I can find this out right away. Mass of the water, oh, I only have the volume of the water. What are we going to do? Oh no, we are going to realize that water has a standardized density. Remember, the density of water is 1. 1 what? Well, 1 gram per cubic centimeter. Or if you like, 1 kilogram per liter. A lot easier to remember that. This is 1 kilogram per liter. It's 1,000 kilograms per cubic meter because there's 1,000 liters in a cubic meter, which is astounding if you really stop to think about it. A cubic meter, like what's a meter? Meter's about like that big, right? A cubic meter's worth of water weighs over 2,000 pounds, over 1 ton. And that's just a small volume. That's seemingly a fairly small volume of water. I don't know. I find that pretty surprising. Anyways, water, liquid water, goes in at 1 kilogram per liter. So I've got 10 kilograms of this stuff. I've got 1 kilogram of that thing. I mentioned before, the specific heat of water is generally taken as a known, and the specific heat of water is it would be 4.2 joules per gram per centigrade. Okay, so remember that we talked about the equivalent heat to work, the mechanical equivalent of heat, And that's because that 4.2 joules is a calorie. So what that means is it takes 4.2 joules to heat every gram of liquid water by 1 centigrade. Okay. You'll often see this as 4,200 if you go to the kilograms, right, or something like that. But nonetheless, we have grams, so we could do kilograms. We could also do really fun things here, like we could put kilojoules per kilogram like that. Just put a K top and bottom, and then that takes care of our kilogram problem. And the delta T's we know for water, it's just the 1.3 increase, and for the metal, it's 80 and it's 21.3. So it's going to be about a almost 60 centigrade loss. But notice that's why the minus sign is here, because when I do delta T for the metal, it's final minus initial, and final is that one, and initial is that one. So we're going to get up a negative number here, and that is why that's there, in order to get that out of here. All right. So what we'll find is that this is equal to a negative of mass of the water, which is 10 kilograms, C of the water, which is 4.2 kilojoules per kilogram per centigrade, and then 1.3 centigrades is the total temperature change of the water. I'm going to find that the mass of the metal is 1 kilogram, and the temperature change is negative, well, it'd be 21.3 minus 80 centigrades. So that's 1.3 less than 60, so 58.7. This would be negative 58.7. All right, and so when I calculate this all out, so that negative should cancel with that negative, and I think I did find a number here which is about 0.93. Question is, of what units are we talking here? Well, if I look at everything else, right, the kilograms here are going to cancel with the kilograms here, centigrade, centigrade. So I'm going to end up with whatever units I put into the original specific heat up here. So it could be kilojoules per kilogram. It could be joules per gram. I'm just going to leave it as joules per gram, centigrade. And so we look up in our table, and as I mentioned by slipping up beforehand, that is in fact the specific heat of aluminum, which is 0.93, or if you like, 930 joules per kilogram, et cetera, et cetera. So we can identify the material by doing a quick experiment like this, which is known as calorimetry. And it's a very quick and easy way to find the specific heats of substances, and also to find how much energy you can increase, or let's say this, how much energy something can increase the temperature of water by. Okay, and this also is how they often deduce the energy content in food. They will basically bomb the food and see how much does that food increase the temperature of water, and then they'll say, oh, okay, well, it gave up this much heat, and therefore it's that many calories, right? So that's one reason why we still operate in calories for food, because of the association with the heat that is given up by these foods in the bomb calorimeters. And then they say, well, it's that much energy, so it's that much food energy. Okay, so there's that. And the next thing to do here would be to say, okay, well, what would happen if we thought about a phase change? Okay, it's not going to happen in this case, because hot aluminum is going to be a metal, solid metal for a lot of high temperatures. But it will easily happen if we consider ice. Okay, so what if we go to ice and we go to liquid water and we say, okay, well, now I'm going to put ice into this liquid. What's going to happen, right? Is the ice going to melt? Is the liquid going to freeze? Is it going to kind of melt a little bit? Right? What's our final state? Okay, what's the final state going to be? So I think we might have at least time to set that up. So let's do that. Alrighty. So same basic idea as before. I'm going to make the same assumptions, which if you ever put ice into a glass of water, you will notice that this is not a great assumption because you'll notice condensation on the outside of the glass. But nonetheless, let's suppose that we have ice into liquid water. Okay. Let's assume reasonable values here. So I have a cup of water, okay, and I'm gonna, like I said, assume that it's nicely insulated. I've got a thermos cup here, okay, I've got liquid in here, and I'm gonna set in some ice cubes. Okay, so let's assume reasonable values for these things. For example, the ice, I have 2 cubes worth of ice, and each one at 30 grams. Okay, so let's suppose I got that. I'm going to have just taken them out of the freezer, so the ice's initial temperature is going to be something like maybe -10 or -15 centigrade. So let's say their initial temperature, sure, let's say -15 centigrade. Okay, it's out of the freezer, and the freezer's job is to make ice, so its temperature has to be less than 0, because if it was 0, then the liquid would just cool down to 0 and still be a liquid, right? It has to continue to take heat out. So let's do that. We're going to know, we can look up what the specific heat of ice is, so we'll call that a known. But I want to go back to here. Let's go to the liquid. The liquid, let's say we have a standard, let's suppose we have a standard amount of liquid, like 200 milliliters, which is what? Slightly less than 8 ounces, 200 mils, 250, so like 250 mils? No. Something like that. Anyways, suppose we have 200 mils, and let's suppose it's at 25 centigrade. And once again, we know the specific heat of the liquid. The question is, when we put ice into here, really, what's the final state? We have to try and deduce what is the final state of the ice and liquid mixture. So, for example, what are some possibilities? Well, I mentioned before that one thing that could happen is the ice could completely melt and then warm up, and the liquid water temperature drops but remains above 0. Okay? So that's a situation in which the ice fully melts and then warms up to the temperature of whatever the water is, the liquid. Another situation would be the exact kind of opposite of that, which is the ice melts a little bit, but it's taking in heat from the liquid, but it's taking in heat enough to the tune that the entire thing freezes. So I'm left with a complete chunk of ice here, right? Something in between those two. This melts, but doesn't completely melt, right? So that the final temperature of this is all at 0 centigrade. Or you could say that the ice causes the liquid here to freeze, but not completely. It might not totally freeze. There's still a little bit of liquid left over, so the final temperature of that would also, again, be 0 centigrade. So we have a couple of different places we could end up. How do we figure out which one it is? How do we get there? All right, how do we get there? Well, I think what we're going to do is save that for next time, because I think that's about the end of the class today. So I will say, enjoy your warm day. And it seems as though our weather knew that we were talking about thermodynamics, because here comes the heat. Now we got to get you to work. And that way your internal energy change might stay the same, or zero, or whatever. Your temperature should stay the same. Well, anyways, we'll pick up here tomorrow, and I hope you have a great rest of your day. Try to stay cool out there. Until next time, folks.